Good morning everyone. My name is Kamalnath. I am pursuing my bachelor's degree in electrical and electronics engineering. Today I am going to share my learning experience from the Emertxe automotive embedded internship. This internship gave me practical exposure to embedded systems, automatic software development, stm32 programming and ADAS concepts. It helped me understand how software and hardware work together in modern electrical vehicles. During this internship, I worked on an electric vehicle ADAS dashboard using the stm32 blue pill microcontroller. The complete project consists of three major stages. The first stage is sensor acquisition, where ultrasonic sensors, potentiometers and other input devices collect real-time data. The second stage is the stm32 firmware, where the microcontroller processes all the sensor information, like it collects all the data from the sensors and then it performs vehicle control, collision detection and fault handling. The third stage is the Python dashboard, which receives data through UART communication and displays vehicle parameters such as speed, battery SOC, obstacle distances and ADAS warnings. So the overall data flow is sensors send data to the stm32 microcontroller, then it goes to the UART communication, then it will show in the Python dashboard. So this helped me understand the complete embedded system workflow from the hardware to software visualization. One of the biggest outcomes of this internship was learning embedded firmware development. I learned to program the stm32 microcontroller using the C programming language and the stm32 HAL library. I worked with several peripherals including GPIO, ADC, timers, PWM, UART communication and DMA. Using stm32cube Emertxe, I learned how to configure peripherals such as timers, UART baud rates and ADC channels. I also integrated HC-SR04 ultrasonic sensors and learned how distance is calculated using the ultrasonic pulse timing. Another important concept I was learned interrupt-driven programming. Instead of continuously checking the sensors, interrupts allow the processor to respond efficiently whenever an event occurs. On the software side, I developed a Python dashboard using the PySerial and a matplotlib, which displayed sensor values in real time. And next, the concepts I mastered. During this internship, I learned several important automotive concepts. The first was the vehicle state machine, where the vehicle changes between different operating modules such as parked, ready, driving, like that. And next I learned about advanced driver assistance systems, it means ADAS, commonly known as the ADAS. This included forward collision warning, blind spot detection and time to collision calculations, like calculating the time of collision happening, which are important safety features used in modern vehicles. I also learned the basics of electric vehicle dynamics. This involved speed calculation, torque estimation, battery SOC estimation, and regenerative braking and different driving modes such as eco, normal, and sport. Finally, I learned structured UART telemetry communication, where sensor information is transmitted from stm32 board to Python dashboard in an organized data format. The next one is tools and development environment. Throughout the internship, I used several industry standard tools like stm32 blue pill microcontroller. For obstacle detection, I used three HC-SR04 ultrasonic sensors. The firmware was developed using stm32cube IDE along with stm32cube Emertxe for peripheral configuration. For visualization, I used Python along with PySerial for serial communication and matplotlib for creating the live dashboard. I also worked with the picsimlab, which allowed simulation and testing before hardware implementation. One interesting thing I learned was how these tools relate to the automotive industry. For example, STM32 acts like a ECU, which means electronic control unit. UART communication is similar to CAN communication, which means CAN communication. picsimlab is similar to hardware in the loop testing, and the Python dashboard represents a human-machine interface used in vehicles. Next, the key learnings and takeaways. This internship taught me much more than just programming. I learned how real-time embedded systems are designed to meet strict timing requirements. I understood the importance of safety critical programming by implementing fault detection, priority-based alarms, and safe operating conditions. I also learned how to build a complete embedded pipeline from sensor acquisition to firmware processing and finally to software visualization. Another valuable lesson was modular programming. Instead of writing everything in one file, the project was divided into multiple mini modules such as EV control, ADAS, ultrasonic sensor, fault handling, and UART communication, making the software easy to maintain and test. Overall, this internship gave me practical exposure to automotive embedded engineering and strengthened my interest in this field. To conclude, the Emertxe automotive embedded internship provided me with valuable hands-on experience in embedded systems, STM32 programming, automotive software development, and real-time communication, and ADAS technologies, which means automated driver assistant system technologies. It improved both my technical knowledge and practical implementation skills, and I believe this learning will help me in further future embedded systems and automotive engineering projects. Thank you very much for giving me this opportunity to share my internship learning experience. Thank you. Now we will see the complete demo of our project. This is the stm32cube IDE, and I have included all the files like header files and footers in this IDE. As you can see, these are all the files, and this is the code we have generated, like header files and the other codes like the sensor input, outputs. This is the clock configuration, and this is the pinout and configuration. Here we are configuring our pins in the STM32 board like ADC, UART and GPI4 pins. We are configuring all those pins here. Then the next one is timers. Then the next two timers we are having connectivity, universal serial like USART. Then the clock configuration, we are using HSE here. Input frequency is 8 and we are multiplying it by 9, so we get the final value of 72 MHz. And this code is generated after the pins are configured by clicking the generate code or by saving the project. Then we are building this project, which means we have built a binary file with 0 errors, with 0 warnings. Then we opened the STM, which means Pixim simulator, and we have the board STM32F103C8T6 board, and operating frequency is 8, and we are loading our binary file here, which is the EV dash we have already stored. When we loading our binary file, we have these components, while the potentiometers and ultrasonic sensors and the displays, which means virtual terminal. These are all the potentiometers, like a temperature bake. So these are all the components, and this is the virtual terminal where we can detect the faults. For example, when we increase the motor temperature, it will show the yellow indication. It will take some time, and here we are seeing the yellow indication, and in our virtual terminal also we are getting the fault 0.01 because we have coded like that in our Q code. Let me see. When the motor over temperature, it will print the fault underscore 0 TS01, and the battery critically low, it will show the fault 02. When the collision is critical, it will show the fault S04. Here we see we can adjust the distance of the vehicle front, left and right. These three sensors are placed in the three different sides of the vehicle. When the distance comes below 30, and then it will be critical for our vehicle because the collision will happen. So this is how our final dashboard look like iBird view with the front vehicle and our vehicle, and it will show the EV metrics like torque, acceleration, brake, motor temperature, alarm, fault and signal. And the speed history, we can see the history of our vehicle speed also. When we increase or decreasing the accelerator, for example, while we decreasing our accelerator, the speed of our vehicle will also decrease. Here in this, it will decrease slowly as the speed of the vehicle decreases slowly. Here also the speed is decreasing very slowly. This is the right side obstacle. It may be car or any other object. When it comes to below 30 centimeter, it will give an advisory alarm. When it comes too further than that, then it will give us a critical alarm. So totally we will get two types of alarms: advisory alarm and critical alarm. It's same for all the three directions: front, right and left. Here we are seeing our advisory alarm. In alarm status, it is showing advisory. When it comes further closer, it will show critical. Our vehicle speed history also changed now. So through this internship, I learned a lot of things in embedded systems like EV ADAS dashboard, how a EV advanced driver assisted system is working. Thanks to the Emertxe team who had taught all of this to me. I had a great opportunity to learn all this. I like to continue further many internship like this from Emertxe. Thank you.